Okay, so now that we've discussed Banach spaces and their duals in general, it's about time we look at an example. We'll do something a little more concrete. So we'll be looking at LP spaces, which are the quintessential examples of Banach spaces. They form a scale of spaces indexed by a parameter p that we take between 1 and infinity. We'll also include infinity in our definitions. And they're defined as equivalence classes of functions up to almost everywhere equality on a given measure space. So what's the definition? I expect you've seen it before, but let me remind you. Lp of omega is the set of measurable functions from omega to r. Measurability is included in the next part of the definition, such that the piece power of the function, or its absolute value, is integrable. Right, so measurable functions with some integrability property. L1 is literally the space of integrable function. LP is the space of functions which piece power is integrable. And the norm that we're going to put in that space, we'll prove it's a norm in a few minutes, is defined as follows. You take the integral of the piece power, which exists by definition, and you raise that to the power 1 upon p. Now, of course, there's one of these spaces that you're very familiar with. It's L2, which is a Hilbert space, and then you already know this defines a norm for p equal 2, and this comes from an inner product. When p is not 2, LP is non-isomorphic to a Hilbert space, but we will see that it's a nice Banach space. And we'll be particularly interested in understanding what the dual of that Banach space is and what linear functionals look like. Okay, so I need to also mention what L infinity is. So in the case p equals infinity, the definition is a little different. We're not asking for the infinite power to be integrable. We're asking for the function to be measurable and essentially bounded. That is to say that there exists a constant that bounds the function, maybe up to a set of measure 0. Right? That makes sense. We're not just asking for the function to be bounded everywhere, because the whole theory of LP spaces, all of measure theory, is built on identifying objects up to almost everywhere equivalent. So if you throw away a set of measure 0, it really shouldn't matter what happens to the representative of your equivalence class on that set of measure 0. So that's the definition, and what we will see defines a norm on L infinity is the infimum of those constant that bounds the function almost everywhere. Now, the key thing we're going to do in this chapter is show a concrete example of the duality of Banach spaces we've been discussing before. So we'll be computing the dual of LP, and we'll see that the dual of LP is LP prime. And what is P prime? It's the conjugate exponent of P, and it's defined in that way. P divided by P1 by P minus 1, as long as P is not 1. And when P is 1, then we'll define 1 prime to be plus infinity. So we'll see that the dual of space of integrable function is the space of essentially bounded measurable function, L infinity, and we'll see that the dual of LP is LP prime. In particular, do notice that 2 prime is 2. So we'll recover the fact that the dual of a Hilbert space can be identified with itself, and p equal 2 is the only value that will solve the equation p prime equal to p. Right? You can check that out from the definition. And notice also from the definition that 1 upon p prime is the only number that solves the equation. 1 upon p prime plus 1 upon p equal 1. So there's a convexity relationship between the two. That's going to be helpful. Now, we could be developing all of our results on LP spaces on any measure space with just a tiny bit of measure theory. All of the proofs that I'm going to do would work for very general measure spaces, but I'm only going to focus on the case where omega is r, right? So what I'm going to be calling LP is really just LP of r. Now, is that a cheat? Am I only looking at a very special LP space? The answer is no. From the point of view of Banach spaces, the LP spaces are almost all the same. The only real difference depends somewhat on the cardinality of your space omega and whether or not your measure has what we call atoms. So it can give a non-zero measure to a point or not. So essentially, when you start having atomic measures and when you start having, say, a discrete omega, then you get the sequence space analog of the space of function LP. And whenever you have a reasonable non-atomic measure on a measure space, then isomorphically as Banach spaces, your LP spaces will just be isomorphic versions of LP of R. So because of that, we're only going to focus our attention in this chapter, which is an example chapter anyway, on LP of R. Nevertheless, I just wanted to point out to you, although I won't really prove it because this will be more measure theory than functional analysis, a theorem that explains what I just say, turn what I just say into a proper statement about isomorphic properties of LP spaces. So let's have a quick look at the theorem 6.2 before we get started with proving that LP is indeed a Banach space. So what theorem 6.2 tells us is that if your measure space happens to be a complete metric space, it's very often the case, right? You're looking at R or RD or a domain of RD or a Riemannian manifold, a domain thereof in partial differential equation. And the sigma algebra you're considering is the Borel sigma algebra. Again, that's extremely common, at least in sort of geometric applications. And you have a measure that is what we call non-atomic, so it gives measure 0 to every point. Again, that's pretty common in geometric situation. That's quite different in probabilistic situation where both atomic measures and sigma algebras that are not Borel sigma algebras are very common. But okay, let's not discuss that here. So if you have that, generic complete metric space as your omega, Borel sigma algebra, and a non-atomic measure, then there has to exist a assuming that you have the same cardinality. So if there exists a bijection between omega and R, then there exists a continuous linear bijection between LP of omega and LP of R. So we'll see that this will force LP of omega and LP of R to be isomorphic as Banach spaces. Okay, I'm saying this theorem we won't prove because really it's a direct consequence of a measure theoretic fact that's pure measure theory, so not really the point in this course. But let me just hint at the proof, right? The hint at the proof here looks like this. The measure theory will provide you with a measurable map, let's call it sigma, that's going to go from the Borel sigma algebra on omega to the Borel sigma algebra on R, right? And it's going to be a measurable, of course it's going to live to that, but let's say it goes from omega to R, it's measurable. And what it does is that it will be such that the measure of a set A in omega will be given by the integral over R of the indicator function of sigma of A of x dx. Right, so there exists such a map, and this map is going to be a bijection, it's measurable, and its inverse is measurable. So if you want, it's an isomorphism in the category of measure spaces. And then because we have this isomorphism at the level of the measure spaces, we can lift this to a isomorphism in the category of Banach spaces. And the way you do that is by defining a map that takes a linear combination of indicator function, so a simple function on LP of omega, if you want, and you send it to its version on LP of R. So this T will extend to a continuous linear bijection between LP of omega and LP of R. Right, you can check that this is indeed this is even isometric given the defining property of this map sigma. Right, so I don't want to really get into the details of that. That's just to give you a hint so that you have a better understanding of why when we talk about LP spaces within functional analysis, we're really only talking about two spaces, LP of R on the one hand, which is the quintessential example of an LP space with a non-atomic measure of a Borel sigma algebra, and little LP that we'll discuss later, which is the space of sequences. such that the sum of the elements of this sequence raised to the power p is finite, and that would correspond to the purely atomic case of a measure. And then you can have mixes of the two that gives copies of sums of the spaces, but these are the only possible LP spaces, really. Now, this being said, we're going to forget general metric measure spaces, and in this chapter, our applications will be restricted to the case of R, although the proofs we're about to do, as you would see, would generalize to other measure spaces very easily. So what do we want to show? We really want to show that LP is a Banach space, right? And then once we know it's a Banach space, it has a dual, and we'll compute its dual and identify it with LP prime. Now, already the dual will play a role in even proving that LP is a Banach space in a hidden fashion. That's through Theorem 6.3, which is called Hölder's inequality. And Hölder's inequality is an extremely helpful generalization of Cauchy-Schwarz inequality. I often joke that as an analyst, the first thing you try, you're trying to analyze things, you try and cut them into simpler pieces and analyze the pieces and then put them back together. So the simpler thing you can do is use triangle inequality, right, with respect to some norm. When you do that, you cut into two pieces and you say, well, if I estimate both pieces separately, I can control the size of the sum thanks to triangle inequality. If that doesn't work, then the next thing you can do that's a little bit smarter sometimes than triangle inequality is an application of something like Cauchy-Schwarz inequality. And if you're not in a Hilbertian situation, then what will replace Cauchy-Schwarz is Hölder. And what Hölder tells you is that the L1 norm of a product is controlled by the LP norm of one element times the LP prime norm of the other element. Okay, so let's go and prove this Hölder inequality. Again, I expect that many of you would have seen that before, maybe in probability, maybe in analysis too, but let's just check that again and then prove that we have indeed a whole collections of Banach spaces with the LP spaces. Okay, let's prove Hölder inequality first. Now, Hölder inequality really have very little to do with Banach spaces, let alone with the kind of measure space on which your LP spaces are built. It's really just a consequence of a fact about positive numbers. So I'm going to start with that as a claim. If I have two positive numbers a and b and I look at their product, this is going to be smaller than 1 upon p times a to the p plus 1 upon p prime times b to the p prime. And that's, let's call that 1, and we're going to prove it. This inequality about positive numbers is a generalization of a fact that's kind of obvious when p is 2. When p is 2, 2ab is smaller than a squared plus b squared, of course, because a minus b squared is non-negative. And that's a generalization of that when you don't put the same weights in terms of powers on a and b. So, okay, let's see how that works. This fact 1 is certainly equivalent, if I take the log on both sides, to log of AB being smaller than 1 upon p times a to the p plus 1 upon p prime times b to the p prime. Sorry, log of that. That's because log is an increasing function. And then you can use properties of log and you can make the left-hand side look a bit more like the right-hand side. You can write that as log of a plus log of b, but you might as well raise a to the p. Then you need to divide by p, and you can raise b to the p prime, and you have to divide by p prime smaller than this. And now this looks very much like a convexity type of inequality, right? It's telling us that a certain multiple of log of AP plus 1 minus that multiple log of b to the p prime is smaller by log of, let's call 1 upon p t times a to the p plus 1 minus t times b to the p prime, right? So this is a consequence of log being concave, and it's a consequence of that since 1 upon p plus 1 upon p prime so is a convex combination, so the two numbers add up to 1, right? And log is concave, of course, because its second derivative is minus 1 upon x squared, which is always negative. Right, so the concavity of the log is really just, and the definition of p prime is really why this inequality about numbers hold. Now, once we know that, okay, we're just going to apply it pointwise. You take an f in LP, you take a g in LP prime, you start computing the integral of absolute value of f times g, and you can use the claim to say that this has to be smaller than the integral of 1 upon p times f to the p plus 1 upon p prime times g to the p prime. Sure. I'm not writing dx, okay, I'm on LP of r, it's dx, but it could be d mu. This is really completely independent of the choice of measure space that I'm using, right? And that, so what I've got here, by the way, is 1 upon p times norm of f in LP to the p plus 1 upon p prime times norm of g in LP prime norm raised to the p prime. Okay, now that holds for all f and for all g. So I could replace f by a multiple of f, not a problem. And then I would get that lambda times the L1 norm of f times g is smaller than lambda to the p times the LP norm of f to the p plus 1 upon p prime times norm of g in LP prime to the p prime, right? So I want to optimize this inequality using the fact that the scaling is not the same on the left-hand side and the right-hand side. I want to multiply f by lambda. This scales by the lambda on the left-hand side, but the LP norm, of course, is scaled by a power of lambda to the p. That gives me some flexibility, and then I exploit that flexibility by choosing lambda appropriately. I choose lambda to be the LP norm of g, the LP prime norm of g to the power p prime upon p, yes, I think, and I divide that by the LP norm of f. Let's see what that gives me. So on the left hand side, I now have j to the p prime upon p, divided by norm of f in LP times fg in L1, and this has to be smaller than 1 upon p times my lambda has been raised to the p, so I get g to the p prime times f to the power p, yes, and this is raised to the power p, so divided by f to the p, so these things cancel, and then I get 1 upon p primes times my g p prime. Okay, but remember that 1 upon p plus 1 upon p prime is 1, so this right hand side is exactly equal to the norm g, the LP prime norm of g raised to the power p prime. And now I can multiply by 1 upon lambda on both sides, and I get that the L1 norm of f times g is smaller or equal to the norms of f in LP times the norm of g in LP prime raised to what power? To the power p primes times 1 minus 1 upon p. But 1 minus 1 upon p is 1 upon p prime. So this is exactly the power 1 here. So I get the inequality. So let's prove that LP is indeed a Banach space for all values of p. Now, in order to do that, we have two things to show. We have to show that the LP norm is indeed a norm, and then we have to show that the LP space is a complete normed space for that choice of norm. Now, proving that the LP norm is a norm is very easy. I'm going to leave most of it as an exercise. It's very easy for p equal infinity. The homogeneity is very simple. The only thing that's not completely trivial is the triangle inequality in the case where p is between 1 and infinity. And let me just do this bit. That's a consequence of Hilbert inequality, by the way. So let's do that. So let's take an f and a g in LP, and let's look at the LP norm of f plus g. Let's raise that to the p. This is equal to, or maybe less or equal, I should say, because I have absolute value, to norm of f plus g raised to the p minus 1 times the norm of f plus absolute value of f plus g raised to the p minus 1 times absolute value of g. And then if you apply Hilbert to that, what do you get? you get the integral of f plus g to the p minus 1 multiplied by p prime times f. What am I talking about? This is then raised to the 1 upon p prime, and that's multiplied by LP norm of f. And then you have the LP prime norm of f plus g to the p minus 1 multiplied by the LP norm of g, okay? And now I need to remember what p prime was. I mean, p prime is equal to p divided by p minus 1. So what I have here really is f plus g in LP norm, but this is raised to the power p minus 1. And then that's time the LP norm of f plus the LP norm of g. And now you divide by f plus g LP norm raised to the p minus 1 on both sides, and that gives you your result. So the LP norm is a norm, and the rest is an exercise, especially the case p equal infinity. All right, now that we've done that, let's get to the heart of the matter, which is proving that for this norm, the LP space is complete. There's going to be two cases when p is finite and when p is infinite. So let's start with the case where p is finite. So I have a sequence in LP, which is Cauchy, and I want to show that it converges. So if it's a Cauchy sequence, I can pick a subsequence such that the LP norm of fnk plus 1 minus fnk is smaller than 2 to the minus k for all k, right? You simply pick n0 to be 0 if you want, and then you pick n1 far enough such that, you pick n0 large enough, and then you pick n1 substantially further such that the difference is smaller than 1/2, and then you pick n2 even much further such that the difference with fn1 is 1/4, and so on and so forth. And you can do that because fn is a Cauchy sequence in LP to start with. So start with this Cauchy sequence or subsequence of that Cauchy sequence, and then I want to define Gn of x for all x in R to be the sum from k equal 0 to n of fn k plus 1, maybe I should not call that m, let's call that m, fnk plus 1 minus fnk of x in absolute value. So Gm is a increasing sequence of real numbers. And what can I say about the LP norm of Gm? Well, the LP norm of Gm, just by triangle inequality, is smaller than the sum from k equals 0 to m of the LP norm of fnk plus 1 minus fnk, and that is smaller than the sum k equals 0 to m of 2 to the minus k, which is certainly smaller than 2 for every m. Right, so this is uniformly bounded in LP. So if I use monotone convergence, by monotone convergence there exists G, and it's going to have to be in LP such that Gm tends to G almost everywhere. Right, the almost everywhere limits exist because this here is an increasing sequence of real number. It could not be infinite except on a set of measure 0 because all of the elements in that sum stay in LP with norm less than 2. Right, so whatever the limit is, it has to also be in LP by monotone convergence. So this series has to converge. But now I want to look at the sequence Fn itself that we started with, and I want to argue from there that this sequence has to be almost surely convergent, right? What I'm using here, really, I'm reproving something you've probably done in doing a bit of meta theory. That is to say that whenever I have a Cauchy sequence in LP, I can extract a subsequence which converges almost surely. That is the subsequence. And if I look at Fnk, actually Fnk plus L minus Fnk for any L that is in N, let's say, what can I say about that for any point X? I can say that, well, this is the sum of Fn j plus 1 minus Fnj of X, right, just by telescoping, j running from k to k plus L minus 1. Maybe let's not take L equal to 0 in that. So this is this telescoping sum. So in absolute value, it has to be smaller than the sum of the absolute values by triangle inequality. So it is smaller than Gn, how did I define that? I call that Gk plus L of X minus Gk of X. Right, but my my sequence G is increasing and converging, so this is certainly smaller than G of X minus Gk of X, and that goes to 0 as k goes to infinity. And so since Gk tends to G almost everywhere, F and K has to converge almost everywhere. So F and Kx, let's put it this way, is Cauchy for almost every x. So it has a limit, and let's call the limit f. Let f of x equal to the limit of the f and k x as k goes to infinity for almost every x. All right, and now I'm claiming that this is actually the limit of the fn's in LP. And why is that? So, well, that I have to say that this limit is actually an LP limit. Now, notice that this f of x minus f and k of x, what is that going to be? Well, it's going to be smaller than g of x. All right, because it is, well, let's see what it is. It is really the sum from j equal k to plus infinity of the fnj plus 1 of x minus fnj of x in absolute value, which is smaller by triangle inequality. And we know the limit exists of fnj plus 1x minus fnj of x, which is equal to g of x minus gk of x. So what have we got? We've got that f of x, f has to be in LP, and the LP norm of f is smaller than the LP norm of g. So I have almost everywhere convergence of my sequence f and k to an f that is in LP. My sequence fn was a Cauchy sequence, and so the limits along any subsequences have to be the same. So what have I got? I've got f and k tends to f in LP. Actually, I should say that's by dominated convergence, because f of x, so f of x is smaller than g of x for almost every x, and g is in LP. And so I get that this converges in LP as k goes to infinity by dominated convergence. And so since Fn was Cauchy, any Fn will be close to an Fnk for k large enough. And we get that the Fn minus F in LP has to go to 0, right? If you have a Cauchy sequence and that has a converging subsequence, it has to converge itself. And that concludes the proof in the case where P is not infinity. So we've proven that LP is a Banach space when P is finite. Let's also prove it when P is infinite. And the last thing we have to do is prove completeness in that case. So, okay, same deal. Let's start with a Cauchy sequence in an infinity. What can I say about that? Well, what's the definition? It tells me that for every epsilon, there exists a capital N, such that for all n and m above that capital N, the sup norm Fn minus Fn, the essential sup norm, is smaller than epsilon. Now, what is that exactly saying? It's saying that there exists an N, such that for all n and m greater than capital M, there exists a set, let's call it E and M, in my sigma algebra that has measures 0. Sorry, I'm using the bar sigma algebra of R. Anyway, so the Lebesgue measure of E and M is 0. And for every x in E and M, Fn of x minus Fm of x is smaller than epsilon, right? It's smaller than epsilon up to maybe a set of measure 0. Now, if I have that, what I could do is I could take the union of my E and M, right, over all possible choices of integers n and m above capital N. I'm taking a countable union of set of measure 0. I would still be of measure 0. So I can construct a set, let's call it E epsilon, that has Lebesgue measure 0. That's the union of all these countably many sets of measure 0. And that set is such that for any, there exists a capital N, such that above that capital N, for every x in E epsilon, the union of all the E and M, Fnx minus Fmx is smaller than epsilon. I've given myself a little bit of uniformity here. Now, what I could do, I could even make that even more uniform. I could take the union of all of these E epsilon over a collection of epsilon that's countable. And again, countable families of sets of measure 0 have measure 0. So what I could get is that there exists a set E in sigma that has Lebesgue measure 0, and that is such that for every, let's say, k in n, there exists a capital N, such that above that capital N, for every x in E, Fnx minus Fmx is smaller than 1 upon k. But that is really telling me that there exists an E in sigma that has measure 0, such that for every x in that E, Fn of x is Cauchy in R, right, as a sequence of real numbers. But R is complete, so there exists an E such that, and there exists an F. Now that F is gonna be the limit of my Fnx, the point where is limit. So if my Fnx were for every x in E smaller than a fixed number, then so will my F. So my F will have to be in an infinity such that for all x in E, f of x minus Fn of x tends to 0 as n goes to infinity. And not only do we have that, but we also have the fact that for every k in n, there exists a capital N, such that for all n greater than this capital N, just taking the limit in here as m goes to infinity now, f of x minus f of n of x is smaller than 1 upon k for every x in E. Right, in E. And that's really telling us that the essential soup is going to 0. So outside of a set of measure 0, the supremum over all x in E of f of x minus fn of x is smaller than 1 upon k. So this is really telling us that this is equivalent to saying that f minus fn, so that there exists an f in infinity, such that f minus fn goes to 0 as n goes to infinity in sup norm. So we've finished proving that L infinity is complete with respect to its norm, and that concludes the global proof that LP for every values of p finite or infinite has to be a Banach space.